Welcome to Talk Tensors.
Glad to be here.
Today, we are going to do something a little dangerous. We are going to try and break the linearity of the universe.
Oh, wow.
Or at the very least, the linearity of the machine learning universe.
That is a bold way to start a morning.
Yeah.
But, looking at the paper on the desk today, it's not entirely hyperbolic. We really are looking at a pivotal moment in AI history where the rules of the road just fundamentally shifted.
I always try to match the energy of the parameters we discuss, and today we are dealing with a number that is, frankly, hard to wrap your head around.
It really is.
We are diving deep into the paper that arguably kicked off the modern era of these sparse giant models. The title is Switch Transformers: Scaling to Trillion Parameter Models with Simple and Efficient Sparsity.
A total classic.
Yeah.
This was published by Fetus, Zouf, and Shazir from Google back in 2022, though the work was, circulating in research labs a bit before that. And you are so right about the scale. The headline number here, the one that made everyone spit out their coffee when they first saw the abstract, is 1.6 trillion parameters.
Trillion, with a T.
Correct. And we really do need to pause there because I think we've become desensitized to big numbers. We throw around billions like confetti these days.
You really do.
To put that in perspective, GPT-3, which was the absolute titan of the industry around the time this work was developing, that was 175 billion parameters.
Right.
So we are talking about a model that is nearly 10 times the size of GPT-3.
And usually when you say 10 times the size to an engineer, they start sweating. They start calculating the electricity bill.
Oh, yeah.
They assume that means 10 times the cost, 10 times the training time, and, 10 times the number of GPUs melting in the server rack. But that's the real hook of this paper, isn't it?
That is exactly the hook. For a long, long time, the scaling laws of deep learning were, they were cruel but fair. It was a linear transaction.
Pay to play.
Totally. If you wanted a smarter model, you added more parameters. If you added more parameters, you had to do more math for every single word you generated. You pay more, you get more. Simple.
And this paper essentially says, what if we could have the parameters but not pay for all of them all the time?
Precisely. It's the difference between having a library of 1 million books and forcing a student to read every single one of them just to answer a simple question. Versus having a library of 1 million books and the student knowing exactly which one book to pull off the shelf.
I love that analogy. It's so clear. So our mission for this deep dive is to figure out how they managed to increase the parameter count by, in some cases, a factor of 100 without exploding the computational budget. We're going to unpack the switch in Switch Transformers, understand why this idea of routing tokens is the secret sauce, and, this is my favorite part, we are going to look at the engineering heroism required to keep this thing from just crashing.
And it really was engineering heroism. This paper isn't just about a new architecture. It's a masterclass in distributed systems, numerical stability, and debugging at a scale that very, very few humans on Earth ever get to experience.
Okay, so before we get into the nuts and bolts of the switch itself and the routing algorithms, we need to set the scene. Take us back to the pre-2022 landscape. What was the status quo that these researchers were trying to overthrow?
The status quo was dense scaling. We were living in the era of the dense transformer, models like BERT, T5, and of course the early GPTs.
Okay, so define dense for us in this specific context.
Dense means that for every single input token, so every word or piece of a word that you feed into the model, every single parameter in the network is activated.
Every single one?
Every one. It all gets used every time.
So if I ask the model, what is 2 plus 2, the entire neural network, all 175 billion parameters of GPT-3, has to wake up, stretch, and fire.
Exactly. It's incredibly inefficient if you think about it. Imagine you have a corporate board meeting with 100 experts sitting around a table.
Okay.
You have a mathematician, a poet, a biologist, a mechanic, a lawyer, the whole crew. In a dense model, if you ask, what is 2 plus 2, you force the poet, the biologist, the mechanic, and the lawyer to all stand up, discuss the problem, do the calculation, and vote on the answer.
Even though the poet has absolutely no idea what they're doing with arithmetic, they're just burning calories.
Exactly. Even though their contributions, their weights, might be effectively 0 for that specific task, you still have to perform the matrix multiplication. You are burning energy and time for parts of the brain that are completely irrelevant to the task at hand.
You're paying for capacity you aren't using.
Perfectly put.
And this brings us to the Kaplan scaling laws from 2020, which were sort of the iron laws of AI at the time, right?
Right. Kaplan and his colleagues at OpenAI basically proves what everyone suspected. bigger is better. There's a power law. If you add compute, you add data, and you add parameters, the loss goes down. The model gets smarter.
It was this beautiful, predictable straight line on a log plot.
It was. But we were hitting a wall, a very real physical wall. We were literally running out of electricity. Training these dense models was becoming prohibitively expensive.
I remember reading reports that training some of these models consumed as much energy as a small town does in a year.
Easily. And that's not even counting the pooling costs.
Yeah.
So researchers started looking for a way to decouple parameter count from compute cost.
Okay.
They wanted a model that had a huge brain, a huge capacity for knowledge, but only used a tiny fraction of it at any given moment. This is the mixture of experts or MOE lineage.
Now, MOE wasn't brand new with this paper, right? It wasn't invented in 2022.
No, not at all. The concept goes back decades, really to the early 90s with people like Jacobs and Jordan. But in the context of modern transformers, the seminal work was actually Shazier et al. Back in 2017.
And Shazier is actually one of the authors on this switch transformer paper too, right? He's a through line here.
He is. He's been chasing this holy grail for a very long time.
So if they had the idea in 2017, why didn't it take over the world then? Why did we spend 5 years building bigger and bigger dense models?
Because the 2017 version was, to put it mildly, a nightmare to train. It was the Wild West of architecture.
How so?
It was just so complex. The communication costs between GPUs were incredibly high. And worst of all, it was unstable. The loss would just spike out of nowhere. The gradients would explode and the model would diverge.
What does that mean, diverge?
It means it just breaks. It starts outputting garbage. NaN is not a number. You'd spend $1 million on a training run and end up with a model that was completely useless.
So it was a high-risk research direction that most people just avoided.
Exactly. Too risky, too expensive, too unstable.
Until Fetus, Zoff, and Shazier decided to simplify it radically. Let's get into the main analysis. The paper is titled Switch Transformers. What exactly are we switching?
We're switching which feed-forward network, or FFN, processes a specific token.
Okay, let's break that down.
In a standard transformer block, you have two main parts. You have an attention layer, and that's followed by a feed-forward layer. That feed-forward layer is usually one giant dense matrix.
That's our board meeting from before where everyone has to speak.
Right. In the switch transformer, they replace that one giant dense layer with a mixture of experts layer. And this new layer contains many, many smaller feed cord networks. For example, in their large models, they might have 128 or even 2048 of them.
Okay, so instead of one big brain, we now have, say, 128 smaller, specialized brains.
Correct. And here is the radical simplification that defines this paper. This is the key insight. In previous MOE papers, the router, the mechanism that decides where a token goes, would usually send the token to the top two or top taught experts.
So if the token was Apple, it might send it to the fruit expert and the tech company expert just to be safe.
Exactly that. The intuition was that you needed at least two experts to compare results or to help with gradient flow. It felt safer, you know? It's like getting a second opinion from a doctor. This paper asks a very provocative, very simple question. What if we just route to one?
1K off, the Highlander strategy. There can be only one.
It sounds so trivial, doesn't it? Just change a parameter from 2 to 1 in the code. But the implications for the system architecture are absolutely massive.
Okay, walk me through the benefits. Why is routing to just one expert so much better than routing to two?
Okay, so first, it drastically reduces the router's own computation, which is a small win. But more importantly, it has the batch size that each expert has to deal with.
What do you mean by that?
If you route to the top two experts, you are physically sending 2 copies of every token's data around the network. If you route to top 1, you only send 1.
And in distributed training, where these experts live on different physical chips, maybe even in different racks in a data center, moving data around is usually the biggest bottleneck.
Exactly. We call it all-to-all communication. It's the traffic jam of the AI world. By going from K to 2 to K to dollar, you cut that traffic literally in half. It simplifies the communication cost across all the devices. It creates a smaller memory footprint on each chip. It allows you to squeeze more experts onto the hardware because each individual expert is dealing with less traffic.
But does it work? My intuition tells me that relying on a single expert is risky. If the router makes a mistake and sends Apple, the fruit, to the car mechanic expert, there's no backup.
Right.
The signal is lost. The car mechanic looks at Apple and says, I don't know, change the oil.
And that was the fear. That was why people use top 2. But what the paper shows is that with enough training, the router gets very, very good at this classification task, this hard switch committing to just one path. It doesn't hurt the model's performance compared to top two, but it saves a tremendous amount of compute.
So the router just learns to be decisive.
It learns to be decisive, yeah.
Let's unpack the router itself then. It feels like this magical traffic cop. How does it actually make the decision? Is it like a whole other neural network?
It's surprisingly simple. It's basically just linear algebra. The router has a set of its own trainable weights. Let's call it $2 hours. It takes the incoming token representation, $6, which is just a vector of numbers, and it multiplies it by these weights.
Right.
And that multiplication gives you a set of logits or raw scores, one score for every expert.
So it's like expert A gets a score of 5, expert B gets 100, expert C gets magnitude 2.
Precisely. Then it just applies a softmax function to those scores. Softmax is a standard function that just takes those raw numbers and squishes them into a probability distribution that sums to 1.
So after softmax, you might get something like expert A, 1%, expert B, 98%, expert C, 1%.
Yep. And since we are doing K$1 routing, the router just picks the winner. It picks expert B. The token is packed up, shipped off to expert B.
And expert B does its thing, processes it, and sends the result back. Okay, I see a potential problem here. We could call it the popular kid problem. What happens if the router decides that expert B is just really, really smart? Or maybe just got initialized with lucky weights and starts sending every single token to expert B?
That is the single biggest failure mode of mixture of experts. It's called mode collapse or representational collapse.
Mode collapse.
Yeah. If 90% of your tokens go to expert B, two very bad things happen. First, expert B runs out of memory and crashes because it can't handle the load.
It's getting a denial of service attack from its own router.
Exactly. And second, and maybe worse, the other 127 experts are just sitting there doing absolutely nothing. You've effectively turned your sparse, massive model back into a tiny, dense model.
You've wasted all your parameters. All that potential is just sitting idle.
Completely wasted.
So the authors have to find a way to force the router to play fair. They introduce what they call an auxiliary load balancing loss.
Right. Auxiliary just means it's an extra loss term added on top of the main goal. So the model has two jobs. Job 1 is the usual, predict the next word correctly. Job 2 is a new one. Spread the work out evenly among all the experts.
How do they formulate that mathematically? Can you explain it in plain English?
I can try. They define a loss function that looks at two different vectors. The first vector, let's call it $5, is the fraction of tokens that were actually dispatched to each expert in a given batch of data.
Okay, so $5 is reality. It's what actually happened.
Right. The second vector, we'll call it $pi, is the fraction of probability mass the router wanted to assign to each expert. So it's the sum of those softmax scores we talked about.
So $pi is the router's intent.
Exactly. The loss function is designed to minimize the dot product of these two vectors. Now, without getting too deep into the vector calculus, this dot product is mathematically minimized when the distribution of values is uniform.
Okay.
So it basically penalizes the model if any single expert starts getting too huge a chunk of the probability pi or the token pi.
So it's like a tax on popularity. If an expert gets too popular, the loss goes up, and the gradients come back and smack the router on the wrist and say, hey, send some work to the other guys.
That is a perfect analogy. It forces a uniform distribution across the experts. It makes sure everyone gets a turn. It ensures that all that massive parameter count is actually being utilized over the course of training.
But even with this loss function, perfect balance is impossible, right? Text is messy. Sometimes you just have a batch of data that is really heavy on, say, biology terms.
Right.
The biology expert is going to get hammered no matter how much you tax it. You can't avoid that.
You're right, you can't. And that brings us to the next engineering concept, which is expert capacity.
Capacity.
In a physical system, like a TPU cluster, you cannot have dynamic memory. Yeah. You can't just say, oh, expert A needs more RAM this millisecond. You have to statically allocate the buffer sizes before you even start the training run.
So each expert has a fixed number of seats at its table. You have to decide that up front.
Yes. And they define that capacity using a simple formula. It's the total number of tokens in your batch divided by the number of experts you have.
So it's the fair share?
Exactly, the fair share. And then they multiply that by something called a capacity factor.
The capacity factor is the buffer. It's the extra wiggle room.
Right. If you have a capacity factor of 1.0, you are assuming perfect balance. Every expert gets exactly their fair share and no more. If you set it to 1.25, you are giving everyone 25% extra seats just in case there's a surge.
What happens when the seats are full? Let's say the capacity factor is 1.25, but the biology expert is getting 200% of the normal traffic because we fed the model a medical textbook. What happens to token number 126?
This is the hard, cold truth of hardware. We call it token dropping.
Ouch. That sounds destructive. It sounds like you're losing data.
It does. But if the buffer is full, the router basically puts up a sorry we're full sign. The extra tokens that were assigned to that expert are dropped.
Does dropped mean they are deleted? Does the sentence just lose a word? Does the patient has cancer become the patient had?
No, that would be catastrophic. Dropped in this context just means the token skips the computation of that expert layer.
It skips it.
Yeah, it passes through the residual connection, which is like a shortcut that goes around the layer without being processed by it.
So it passes through completely unchanged. It's like the student showing up to class, finding the doors locked, and just walking to the next class without learning anything new in that specific hour.
That's exactly it. It retains its previous state from the layer before, but it doesn't get the benefit of that specific layer's transformation.
That feels... Well, it feels so optimal. I mean, if I'm a token, I want to be processed. Did they try to fix this?
They did. Yeah. It's great. In Appendix B of the paper, they detail an experiment called No Token Left Behind.
I love that name. It's very No Child Left Behind.
The idea was completely logical.
Yeah.
They thought, okay, if expert A is full, let's just reroute the overflow to the second best expert. Just find anyone who has room. Don't just give up on the token.
Makes perfect sense. It's better to get some processing from the chemist than no processing at all because the biologist was busy.
You would think so. But surprisingly, it didn't help performance.
Really?
Yeah. It added a lot of complexity. It messed with the gradient signals because now you are routing based on availability rather than expertise. And the model didn't actually learn any better.
That's so counterintuitive.
It is. But it turns out just letting the token skip the layer is totally fine, provided your drop token rate is low. Typically, they would tune the capacity factor to keep the number of drop tokens under 1%.
So the network as a whole is robust enough to handle a little bit of skipped homework here and there.
The residual connection is a powerful thing. It carries the information forward regardless. The model learns to be robust to it.
Okay, let's pivot to the secret sauce. We mentioned earlier that these old MOE models were notorious for just blowing up diverging during training. You spend $1 million on compute and get NaN, not a number, as your loss. How did they stabilize this beast?
They implemented a few specific engineering fixes that are just crucial for anyone trying to train these things today. These are the kinds of details that usually get buried in footnotes, but are actually the difference between success and total failure.
Okay, lay them on me.
The first one is called selective precision.
This is dealing with the different kinds of numbers, like float 32 versus bfloat 16.
Exactly. Google's TPUs, their tensor processing units, they love bfloat 16. It stands for brain floating point. It's a 16-bit format that is super fast, very memory efficient, and generally good enough for most of deep learning. But exponentials, like the ones used in that softmax router function we just talked about, can be very, very sensitive to low precision.
Sensitive?
Well, if you have a large number entering an exponential function, the result gets huge very, very fast. If you do this in low precision, like 16-bit, you can get rounding errors. You might get infinity or just noise.
So if the input to the router is noisy, the routing decision becomes totally random.
Yes. The router goes crazy. It starts sending tokens to random places, the load balancing is shot, and the whole thing can collapse.
So what was the fix?
Their fix was to cast the router calculations to float 32 high precision, but keep all the rest of the massive matrix multiplications in the experts in the fast bfloat 16 format.
So the brain of the operation, the router, wears glasses to see clearly, but the muscles, the experts, they can work on instinct and speed.
That's a really good analogy.
Yeah.
It stabilized the softmax without incurring the huge computational cost of full precision everywhere. The router is a tiny, tiny part of the overall compute, so you can afford to be very precise there.
Smart. What was the second big fix?
Initialization scaling. This is all about how you set the random weights of the network before training even starts.
Right. Usually you just initialize weights with some kind of normal distribution, right?
Yeah.
A bell curve centered on 0.
You do. And the standard transformer initialization usually sets the weights with a certain variance, often scaled by a factor of $1. But in these massive sparse models, they found that the initial random noise was just too loud.
Too loud?
Yeah. Because you have so many parameters, the signal-to-noise ratio at the very beginning of training was terrible. The experts were all just shouting random numbers over each other before they had a chance to learn anything.
So they just turned the volume down on the initial noise?
Drastically. They reduced the variance scale from $7 all the way down to $7.14, 10 times smaller.
That seems really aggressive. Usually if you initialize your weights too small, the network doesn't learn because the gradients vanish to nothing.
It is aggressive. And in a dense model, it might not work. But here, it was the key to preventing those early instabilities. Smaller initial weights meant the gradients didn't explode in the first few thousand steps of training.
So it allowed the model to gently wake up rather than being jolted awake with a fire alarm.
Exactly. It gave the router time to learn some basic patterns before the experts started pushing these massive values through the network. It was a crucial stabilization technique.
I want to touch on the distributed training aspect briefly because I think people really underestimate the complexity of splitting 1 trillion parameters across a warehouse full of chips. You can't just load this onto a USB stick.
No, you cannot. This entire project relies on a library they built called Mesh TensorFlow. And you have to think about 3 different dimensions of parallelism at the same time. It's like a 3D puzzle.
Okay, break them down for us. What's dimension 1?
Dimension 1 is data parallelism. That's a standard one everyone knows. Everyone has the same model. But chip A works on the first 100 sentences of the data set. Chip B works on the next 100.
Got it.
Then they all talk at the end and average their learnings.
Easy enough. Standard practice for years. What's dimension 2?
Second is model parallelism. This is when the model itself is too big to fit on one chip. So chip A holds the first 10 layers, and chip B holds the next 10 layers. Or, more commonly, chip A holds the left half of a giant matrix, and chip B holds the right half.
Okay, so you're splitting the brain itself across different physical locations.
Correct. And the third dimension is expert parallelism. This is the new one from the switch approach.
Right.
In this setup, all the chips have the same skeleton of the model. The attention layers, the residual connections. But chip A holds the weights for expert 1, chip B holds the weights for expert 2, chip C for expert 3, and so on.
So when a token that's currently being processed on chip A decides it needs to talk to expert 2,
it has to travel. That token's data has to be packaged up and sent over the physical interconnect wires from chip A to chip B. Chip B then processes it using expert 2's weights, which live exclusively on chip B's memory, and then sends the result back to chip A.
That sounds slow. Physics is the enemy here. The speed of light is the limit.
It is, if you aren't careful. And that's why the K.O running is so critically important. It minimizes that travel traffic. If you had to send that token to 5 different experts living on 5 different chips, you just flood the interconnects and grind the whole system to a halt.
The paper mentions 2 big models they trained, Switch C and Switch XXL. What's the difference between them? They both sound absolutely enormous.
They are. Switch C was the parameter monster. That was the 1.6 trillion parameter model. It used pure expert parallelism. It was designed to maximize sheer size. It had a huge number of experts, 2048 of them, but each expert was relatively standard sized.
And Switch XL?
Switch XXL was designed to be the smartest model, not necessarily the biggest. It actually combined expert parallelism with model parallelism. It was smaller in total parameters than Switch C, but it had much larger, much denser computations per expert.
So Switch C is like the library with the most books, but Switch XXL is the library where the individual books are written by geniuses. They're denser.
That's a great way to think about it. And interestingly, Switch XXL was actually harder to train because of that density. The immense amount of compute per token made it more unstable than the bigger, more sparsely activated Switch C.
Fascinating. So let's get to the scoreboard. We've built this massive, complicated, sparse machine. We've stabilized it. Did it work? Was it worth it?
Resoundingly. It absolutely changed the trajectory of large model research at Google and really everywhere else.
Okay, give me the numbers. What's the headline stat?
The main headline stat is a 7x increase in pre-training speed compared to their dense baseline, which was T5 base.
7 times. So if T5 took a week to train to a certain quality, this takes a day.
Effectively, yes.
Yeah.
To reach the same level of quality or perplexity.
Yeah.
And you have to remember, this is with the same computational resources, the same FLOP's budget. They didn't just use a bigger computer to get that speed up.
Right.
They just used a smarter architecture.
That is the magic of sparsity. You are getting free speed. It's an efficiency game.
They emphasized this point heavily in the paper. They didn't use more compute per token. They used more parameters to make the compute they had more efficient. This is what we call sample efficiency.
The sparse models just learn faster.
Much faster. They soak up information more readily because they have these specialized subnetworks that can latch on to different patterns in the data without interfering with each other.
But pre-training is just, predicting the next word. It's the cat sat on the mat. Great. Can it actually answer questions? Can it summarize a document? What about downstream tasks?
This is where things get tricky. We call this downstream fine-tuning. You take this giant generic pre-trained model and you teach it to do a specific task, like the Super GLUE benchmark, which tests logic and language understanding.
And this is where sparse models usually stumble, right? Historically.
Historically, yes. And just think about it for a second. You have a model with 1.6 trillion parameters. You show it a fine-tuning data set that might only have, 10,000 examples?
It's a recipe for overfitting. The model will just memorize the answers. Oh, I've seen question 42 before. The answer is B. It doesn't learn the underlying reasoning.
Exactly. The model is just too big and powerful for the tiny data set. So the authors had to invent a new regularization technique specifically for this. They call it expert dropout.
Okay, first, can you give a quick refresher on what standard dropout is for the listeners who might be rusty?
Sure. Dropout is a technique where during training, you randomly turn off some of the neurons in the network. You just set their output to 0 for that step.
Why would you do that?
It forces the network to be more robust because it can't rely on any single neuron or pathway to always be there. It learns to store information redundantly. Usually you set the dropout rate to maybe 10% or 0.1.
But for switch transformers, they had to do something different.
They found they needed to be much, much more aggressive, but only inside the experts. They set a standard dropout rate of 10% on all the non-expert layers, but a heavy dropout of 40% inside the expert FFN layers.
40%. So they are practically lobotomizing the experts during fine-tuning to make sure they don't just memorize the data.
Lobotomizing is a harsh word, but yes, that's the intuition. It forces the experts to learn generalizable features rather than just memorizing the specifics of the training examples. If you delete 40% of the expert's brain at random every single step, it has to learn to store information in a really robust and distributed way.
And what were the results of that? Did it work?
It worked extremely well. They achieved state-of-the-art on 101 different languages in their multilingual T5 comparison.
101 languages.
And get this, 91% of those languages saw a 4x or greater speedup over the dense baseline model.
That's massive, especially for low-resource languages that don't have a lot of training data.
It's a game changer for them. Because the model has so many experts, 2048 of them, it can effectively dedicate specific experts to specific languages or language families. It doesn't have to force Swahili and Icelandic to share the exact same neurons. It essentially learns a Swahili expert and an Icelandic expert naturally during pre-training.
But here is the elephant in the room, the practical question. I cannot fit 1.6 trillion parameters on my laptop. I can't even fit it on a standard server rack in my company. I'd need a dedicated warehouse. So how do we actually use this thing in a product?
This is the deployment bottleneck. Serving a sparse model is very hard because you need all that memory available all the time, just in case a token needs to talk to a specific, rarely used expert. But the paper offers a very practical solution: distillation.
The shrink ray.
Exactly. They show that you can take this massive sparse teacher model and use it to teach a tiny dense student model.
How much quality do you lose in that process? Usually the students aren't as smart as their teachers.
Well, they compressed the model by 99%. They went from the sparse giant all the way down to a T5 base size model.
Okay, a 99% compression.
And in doing so, they preserved 30% of the quality gains that the giant model had over the baseline.
Wait, let's parse that very carefully. They kept 30% of the gain, not 30% of the total performance.
Correct. So let's use an example. If the baseline small model scored a 70 on a test, and the giant sparse teacher model scored an 80.
So a 10-point gain.
Right. The distilled student model would score a 73. It kept 3 of those 10 extra points.
That sounds okay. That's actually good. It doesn't sound amazing.
It's actually very, very significant. It validates the train huge, deploy small pipeline. It means you can use the massive sparse model as a knowledge compressor or a reasoning engine during a development phase, and then squash that intelligence into a portable, efficient format for production. You get a better small model than you could have ever trained from scratch with the same budget.
I want to talk about the limitations, though, because we promised a balanced view of the paper. It wasn't all just victory laps and state-of-the-art results.
No, absolutely not. There was a definite reasoning gap.
Explain that. What do you mean by a reasoning gap?
They found that on knowledge tasks, things like trivia QA or natural questions, which are basically about recalling facts, the bigger the model got, the better it did. The 1.6 trillion parameter model was a trivia god.
It had the capacity to essentially memorize the internet.
Exactly. But on reasoning tasks, like the Super GLU benchmark, which requires logic, common sense, and cause and effect thinking, the gains were much less consistent.
So it knew a lot of facts, but it wasn't great at connecting them.
Something like that. In fact, on their very largest, densest computation model, that SwitchXXL, the reasoning performance was finicky and sometimes even worse than smaller models.
Why do you think that is?
The authors themselves admit they don't fully understand it. It points to a blind spot in our understanding of the link between parameter count, FLOPs per token, and true reasoning ability. It seems that just adding more experts gives you more facts, but it doesn't necessarily give you more logic.
Logic might require depth, not width. You need to think longer, not just look up more references from a bigger library.
That is the leading hypothesis, yes. Reasoning requires a longer chain of sequential computation. Sparsity gives you a very wide, but maybe shallow lookup table.
And we also have to mention that despite all those secret sauce stability fixes, the very largest dense flop-matched model, SwitchXXL, was still unstable.
That's right. They note that it couldn't complete the full training run without diverging at some point. The Switch C, the big sparse parameter monster, that one was fine. But the dense computation monster was still too fragile.
We are still at the frontier of numerical physics here. We're pushing the hardware and the math to its limits.
We really are.
There was one other interesting path not taken that they mention in Appendix A, switch attention.
Yes. So all the stuff we talked about was replacing the feed-forward layers with experts. But what if you replace the attention matrices, the query, key, and value projections with experts?
That seems like a logical next step. You could have specialized attention patterns. One expert that focuses on local grammar, another that focuses on long-distance dependencies across a paragraph.
They tried it, and it worked great in Float 32.
Ah.
The moment they switched to the faster, more efficient bfloat 16, which is necessary to do this at scale, it exploded. It diverged instantly, and they couldn't stabilize it.
So the hardware precision just isn't there yet for sparse attention mechanisms.
Or the algorithms need to be more robust. It remains a fascinating open research question to this day.
This paper really did set the stage for so much that came after. Things like G-shard and all the rumors surrounding models like GPT-4 being a mixture of experts.
Absolutely. This paper proved that you could do MOE at scale, you could do it simply, and you could do it stably. It took MOE from being a cute academic idea to being, this is how we build the future of AI.
Okay, we've covered the history, the architecture, the math, the engineering, and the results. Now it's time to get a little weird.
It is time for novel notions.
This is the segment where we take the paper's core ideas and we push them off a cliff to see if they fly. And a quick disclaimer, this is for entertainment purposes only. Please do not try to build a startup based on these ideas without first consulting a psychiatrist.
Or at least a very, very patient venture capitalist.
Okay, idea number one. I call this the expert lottery and dynamic pruning.
Okay, I'm listening.
So we have a Switch C model with, say, 2,000 experts. We train it on the whole internet. But when I want to deploy it, I don't care about the whole internet. I'm a law firm. I only care about legal contracts and case law.
Right, okay. You have a very specific domain you care about.
Currently, we would just fine-tune the whole thing on legal text. But my theory is based on the lottery ticket hypothesis. I bet that out of those 2,000 experts, there are maybe 5 or 10 that are doing 99% of the work for legalese.
That is extremely plausible. We already know experts tend to specialize. One might capture the weird syntax of contracts, another one captures all the Latin phrases.
So, here is the mechanism. We take the fully pre-trained 1.6 trillion parameter model. We run a pass over a massive corpus of legal documents, but we don't train it, we just observe. We record which experts activate for which tokens. We rank them by usage.
You're finding the legal clique, the experts that fire up when they see words like heretofore and indemnify.
Exactly. We identify the top 5 or top 10 experts for that domain. Then we physically extract only those experts. We throw the other 1,990 experts in the digital trash. We ship a legal switch model.
So you are creating disposable experts.
Yes. The result would be a model that is 99% smaller than the parent model, but retains 100% of the expert capacity for that specific domain. It's not distillation, which loses information, it's surgical extraction.
This is really interesting because it bypasses the need for expensive retraining or fine-tuning. You're essentially discovering the subnetwork that learned law and then liberating it from the rest of the brain.
Right.
The main challenge, I think, would be the router. Well, the router was trained to choose between 2,000 different options. If you suddenly give it only 5 options to choose from, its softmax probabilities will go completely haywire. It will try to route a token to expert number 1900, find that it's missing, and panic.
Ah, okay. So we freeze the weights of our 5 extracted experts, and then we just fine-tune the router for a few hundred steps on legal text to make it realize, oh, I only have these 5 friends now. I need to remap my world.
That could work. A router lobotomy in rehab. I like it.
Yeah.
This would allow for things like model marketplaces, where you don't download the whole model, you just buy the specific lobes of the giant brain you actually need for your business.
Exactly. I'll take the medical diagnosis lobe and the Python coding lobe, please. You can keep the 18th century poetry lobe. I'm good.
Okay, what's idea number 2?
Idea number 2 is inspired by the failure of switch attention in the appendix. I call it recursive switch, or maybe fractal attention.
Sounds trippy.
So the paper assumes every expert is the same kind of thing. Expert 1 is a feed-forward network. Expert 2 is also a feed-forward network. They just have different weights.
They're homogeneous experts, yes. Oh,
Well,
correct.
Why do they all have to be the same architecture?
Well, for simplicity.
Yeah,
For making the parallelism work on the hardware.
sure, for now. But imagine this. What if the router didn't just choose which weights to use, it chose which algorithm to use?
Explain what you mean.
Okay, so Expert 1 is a standard transformer block, like in the paper. But Expert 2 is a convolutional neural network, a CNN. Expert 3 is an LSTM, a long short-term memory network. Expert 4 is a symbolic calculator that can do perfect math.
I see where you're going. So for a token that looks like it's part of an image description, the router sends it to the CNN expert. For a token that looks like it's part of a time series trend, it sends it to the LSTM.
And for a token that is literally 2 plus 2, it sends it to the calculator.
Exactly. The model becomes a kind of compiler. It chooses the best mathematical operation for the specific token type on the fly.
This would directly address the reasoning gap we talked about earlier.
Precisely. The reason transformers are bad at math is because matrix multiplication is a terrible way to do arithmetic. It's an estimation. But if one of your experts was just a call to a Python script that does perfect math, problem solved.
The router becomes a neural controller. It's not just routing to knowledge, it's dispatching tasks to specialized tools.
Okay, so what's the fractal part of the name?
The fractal part is this. What if one of the experts is another smaller switch transformer?
Whoa, recursion.
You route the really hard, ambiguous problems to the deep thinking expert, which is just a whole other model nested inside the first one.
You're describing a way to dynamically allocate depth. Easy tokens get processed by a shallow, simple expert. Hard tokens get routed to a deep expert that can perform many more steps of computation.
Adaptive computation depth.
That is actually a very hot area of research right now.
Yeah.
But combining it with heterogeneous architectures, mixing CNNs and transformers and LSTMs, all behind a single switch router, that is the truly novel notion.
It would be an absolute nightmare to engineer on current hardware, though.
Oh, a total nightmare. The CUDA kernels would be a mess. You'd break all the assumptions that allow for efficient batching. But it's a cool idea.
That's why we just talk about it on the deep dive and let the brilliant engineers at Google and elsewhere figure out how to actually build it.
Fair enough. Someone has to do the dreaming.
To wrap up, switch transformers, they really did change the game.
They proved that sparsity is the only viable path to scale to trillion-plus parameter models without bankrupting the global energy grid. They paved the way for G-Shard, for the modern MOE architectures that almost certainly power the chatbots we talk to every single day.
It's the ultimate work smarter, not harder paper. Why use all your brain cells when just one will do the job perfectly?
A lesson for us all, I think.
If you want to read the full paper for yourself, we'll have a link in the bio. It's a dense read about sparse models, but it's absolutely worth your time.
And remember, if your loss curve is exploding and you don't know why, just try dividing your initialization variance by 10.
Solid advice. Keep your gradients stable and your sparsity simple.
Welcome to Talk Tensors.
See you next time.